I'd like to start out this lecture by looking at problem number 1 of homework 3. This is a schematic of the system. We're looking at a DC motor here. There's the shaft. There's no load on the shaft right now. So the total inertia of the shaft is simply the inertia of the motor itself. And the total shaft losses, viscous losses, is just the motor bearing loss. And the rest of this circuit is a 4-quadrant DC to DC converter, or it's an H-bridge power electronics circuit that has the ability to conduct current in both directions and reverse the voltage applied to the motor, which would allow you to, if you had the full capability of this DC to DC converter, you'd be able to ramp up to some speed and then ramp down and even go down to a negative speed. You could produce regenerative power from this motor, which will eventually show you how that can happen, but it has a passive diode rectifier front end, and so that's going to block any current from going into the source, and as a result it will cause some limitations to what you can do, and we'll show what those are eventually. We have a rudimentary description of the controls here, where this is for an open loop controller, so we're going to command ultimately a voltage produced from that duty cycle dA and dB. dB is simply the negative of dA, and that's how unipolar PWM is achieved. Then we have the inverse of HA and the inverse of HB, which turns these two duty cycles into 4 gate pulse commands in order to produce upper and lower commands to each of the phase legs of this H-bridge converter. Now I'm just going to work through problem 1. The first one is very easy. So we have an AC fed full bridge to DC fed unipolar PWM controlled DC to DC converter, and it's driving a DC permanent magnet motor. We're going to only apply open loop controls by ramping a voltage at a rate that will keep the armature current, or at least we hope that will keep the armature current below 1.5 per unit transient current, and then the actual current limit resulting from that would be approximately 144 amps. When we want to limit the armature voltage because of the front end AC voltage, we can't exceed that, and we'll also want to provide some dynamic margin so that when we apply closed loop controls we can achieve everything that we need without saturating the PWM controls. Now we also will be assuming a very large DC link capacitance. We provide that parameter right here at 10 millifarads. So that would create a fairly stiff voltage against which the motor drive can operate. So we have these parameters here, and we have these nominal ratings, and then we have these drive parameters. So the first thing is, in order to, just a moment here, in order to find the DC link voltage, we would take simply square root of 2 in order to get the peak DC on the other side of across the DC link capacitor. So that would be square root of 2 times 460, and the resulting answer is 650 volts. Okay, so now let's go on to the second question asked. What is the steady state armature voltage that would be required to achieve rated current? So I'm going to list what you need to solve this problem. First of all, you need to know the rated current. That's been given. That's 96.5 amps. You also need to know the rated speed in radians per second. So notice that we have been given the rated speed in RPM. So we need to convert that by taking pi over 30 times the rated speed in RPM, and that will give us 188.5 radians per second. So the expression for the armature voltage is the armature resistance times the armature current plus the back EMF voltage. So let's start by finding the back EMF voltage, and that EA under rated conditions is going to be the back EMF constant K sub E times the rated speed. So we know what those are. We have KE is 2.15, RA is 0.15, and we've just calculated the rated speed. So that is 2.15 times rated speed, 405.3 volts. We know that we have a resistance of 0.15, and that's the only other thing that we need to know. So we can solve VA rated as 0.15 times the rated current, 96.5, plus the EAR, which is 405.3, and we get the final result of the rated armature voltage as 419.7 volts. Let me explain exactly what I mean about producing and how to produce a voltage that would be applied to the motor that will ramp up the speed to, say, a commanded value. So what we're really trying to achieve here is we want to start at zero speed, and we want to ramp up to this point here and then be at a desired commanded speed. And we're doing this without any closed loop controls. So this is what we would call our desired speed, omega m star. Now the time to ramp up this to that omega m star, we could call that T ramp omega. What would determine that time is to go slow enough to keep the current, the armature current, below our transient current limit. Here's the armature current here. assuming that we had an ideal system, we could instantaneously get the current to go up to the limit, IA limit. And remember that what IA limit is, and this IA limit would be 1.5, or approximately 1.5 times the rated current. And then we would ideally hold the current there until this point is reached, at which time the current would drop down to whatever current would be required to achieve the speed that we desire. So in this case, what I'm indicating is that in this period of time right here, we're at a steady state speed with some load. If we didn't have any load, then the current here would be dictated simply by the losses on the mechanical shaft. So you might have a very small value of current at no load, and it has to supply the shaft losses. So the question of how we get this is something that we need to answer. The other thing is, why do we need a constant current? The answer to that is that we have a ramp that is linear. If it's a linear ramp, we're going to get to that speed as fast as, well, say under ideal conditions, if we could make the motor do whatever we want it to do, which you'll see that we can't. The closed loop controls will help us make the motor do what we want. But this is a linear slope of the rate of change of the speed with time. We know that during this portion of the ramp, the applied torque to the shaft, TE, is equal to the inertia, the total inertia of the shaft, and if we had connected a load connected, that would include the inertia of the load times change of speed with time. Very simplistically, we could estimate that time if we assume that the numerator of this differential equation is just a change in speed. So in this case, the change in speed we're talking about is from 0 to omega m star divided by a change in time, and that's the t ramp up time. So rearranging this equation, we have delta t equals t ramp up, and that would be equal to the total inertia times the change in speed divided by the required torque. And another way to look at this whole problem is that the slope is simply J total divided by the torque. We know that since we have a linear slope, such as this is omega m during that period of time, the derivative of omega m dt will look like a straight line. This is the derivative right here. So the idea would be to come up with a voltage command that would produce this kind of shape. In general, IA would be equal to the torque that is required to ramp up the speed divided by the torque constant, K sub t. So that's what's happening here. We need to come up with a voltage command that will produce this current. And we're looking at this motor very, very simplistically. We're really not including the dynamics of the motor model other than our assumption that we'll have a constant slope. you'll see that having a constant slope is not going to produce exactly this shape. And without having closed loop control, there's really no way that we can keep the current below this ideal line and avoid going above this transient limit. But what we want to be able to do is we want to come up with a voltage and ultimately a duty cycle command. So we have this duty cycle d sub a that we start everything off with, and that would be simply equal to the required voltage command that we need to synthesize. And I want to point out again, this is a time changing voltage, armature voltage command, and then that is divided by the DC voltage value. We're going to assume it's a constant here, and that's how you get the DA command. So what we will end up getting with the approach we're taking is a voltage that will look just like the speed. Now once we hit the desired voltage that we're trying to achieve, we're at steady state, and the current that we're settling out at here is dictated by the load only. There's no transient involved. If we had no losses, the current would go all the way down to zero at steady state. In our simulation model, we would apply a slope limiter. So we need to find the rising slope, or say so d sub slope, that's the rate of change with time of the dA that we're commanding. So we will want to find this. We need to know T ramp W, and we need to use a motor model to find this value of d slope. So moving on to problem 1c, calculate the duty cycle required to achieve nominal rated voltage. Well, in order to find that duty cycle, we need to figure out what is nominal rated voltage. We've already found what that is, 419.7, and so the duty cycle is going to be dA for rated conditions divided by VDC rated, 419.7 divided by 650, which is 0.645. Next, in problem D, we're asked to find the rated torque applied to the motor end of the shaft for all of the conditions described up above here. So let's look at what we mean. That would be what we're looking for. That is the same as TE rated. You notice that we have a bearing here, which is mathematically described this way, and there is going to be a loss, a torque loss, which is Bm times the whatever speed you're at. That torque loss is at the end of the shaft here, so we would call that T shaft. We would have the TE for rated conditions as the torque constant times the IA under rated conditions. So that's 2.15 times 96.5, or 207.5 Newton meters. So the next question asked is to find the load torque that includes the load and then the torque at the end of the shaft. That would give you the total torque. This T shaft includes TER. So basically what I'm saying is that T shaft is equal to TER plus Bm times the speed. Now we're going to be at rated speed here. And then the resultant load torque, T load, is going to be equal to T shaft. So plugging in what we know, the load torque under rated conditions is equal to the applied torque from the motor, 207.5, plus the damping, B sub m, which is 0.05 times the rated speed of 188.5. And the resultant load torque is therefore 217 Newton meters. So far we have done these three problems here. The final one is going to help us set up the simulation. And it's what I described here. And we're going to utilize this expression here to find the delta t first. So we already know that, and we know therefore we're looking for, as the first part of this, the time it takes to ramp up. That is equal to J total times the delta omega m. Well, that's simply the rated speed that we're trying to get to, divided by the limit torque. So we'll call this TE limit, where TE limit is KT, the torque constant, times the rated current. Let's step back for a moment and describe what we're trying to do, and then I'll finish solving for this slope. Our desire is to ramp up the speed over a period of time defined as T ramp speed, and that should give us the slope of the speed of the torque applied divided by the inertia. And after T ramp omega, we will arrive at the commanded speed omega m star. Now the T ramp omega is defined so that the armature current does not exceed the level of IA limit. IA limit is 1.5 times the IA rated, which is 96.5. So the resultant current for IA limit is 144.75. I had accidentally dropped off this 0.75 before when I set up the problem, but actually this is significant. You could even say it's approximately 145 amps. So the applied torque, or the torque limit, would be the torque constant times IA limit. That's 2.15 times 145 in this case, which is 312 Newton meters. So again, recognizing that the differential equation that would control the acceleration of the motor is TE limit equal to the total inertia times the rate of change of speed with time, or that's the acceleration. And as we said before, we can simplify this, find what we're looking for. TE lim being equal to J total times the change in speed that will occur over the time it takes to ramp up, T ramp of the speed omega. We know that delta omega m is equal to omega m star because we're ramping up from 0, and therefore the equation becomes TE lim equal to J total times omega m star divided by the ramp up time. Rearranging to find an expression for T ramp omega, we have J total times omega m star divided by TE limit. So now we have everything we need to know to find that time. So J total is 1 Newton meter second squared times 188.5 radians per second divided by 312 Newton meters. And that is 0.604 seconds. And what we're after is we're wanting to create this trajectory for the duty cycle, which will feed into the pulse width modulation. And if we can apply this waveform of duty cycle and principally defined by this term d slope, we should achieve this speed trajectory here. So for a moment, let me explain how this could be done in a simulation from a top level, and then I'm going to take you through my simulation. What you do is you're going to start applying a voltage to the motor through the pulse width modulation, and that the averaged voltage should follow this trajectory of duty cycle d of t, which is produced by starting with a initial 0 duty cycle, then commanding a duty cycle which I'll call dA limit. And we'll apply that for the period of T ramp omega. Now how that gets applied that way is that we take these commands just going right from 0 to dA limit, and then when the speed hits omega's m star, we'll apply another command that will drop to the rated duty cycle, and then we're at the steady state, and we're at the steady state speed. But we can't just apply square waveforms to the motor, because there's physics involved here that will limit the rate of rise of current, which would basically be the delta I from, in this case, 0 to IA limit, over a ramp time, which is a function of the armature electrical circuit physics. Then we apply this constant current here, and basically what this represents is this is probably the fastest rate of rise that we could apply to the armature, and without causing a resonant condition. And then as we were holding it constant and at this maximum current, trying to keep the current below what the drive can handle under this transient time of T ramp omega. So in a simulation, we can apply a ramp limiter to the duty cycle, and we need to find out what the slope of that is so that it can go into the ramp limiter. If you were going to do this in actual hardware, it would be done a little differently. You would basically start at 0 and just start counting up in increments associated with, let's say, a time that it takes to execute the math on a given processor, and then just stepping up every time until you hit a calculated point here. It's calculated based on your target speed. We're just pre-calculating this slope and going to use a very simple MATLAB function to create these ramped waveforms, ramping up, ramping down, and so on. So in order to find that, what we need to do is we need to determine what the armature voltage would need to be to achieve the rated speed. And we actually already know that. So recall that we calculated that armature voltage at rated speed using this equation here. Now this is a very simplistic way of achieving what we would call a voltage feed-forward trajectory. So the rated target point is right here. That would be the value, that would be the duty cycle that produces 419.7 volts. But we need to find the duty cycle that would produce a voltage that should keep this current at the IA limit. We'd have a VA limit being equal to RA times IA limit plus KE times omega m star. And then the DA limit would be equal to VA limit divided by VDC. Now I want to introduce a nomenclature at this point. We can't know ahead of time and at all times the exact values of the motor parameters because they'll change, for example, with temperature. But we can estimate them. So if it's an estimate, I'm going to put this little hat over the variable. So there's R sub A, there's KE, and also we'll want to estimate the rated DC voltage, or we could just also call this VDC rated as a parameter in our controller. So we want to recognize that we can never exactly produce these time domain waveforms that will match what the motor is expecting to see because the parameters might change. The other thing that we'll see when I run the simulation is that it'd be impossible to produce these exact waveforms here without any closed loop control. And even with closed loop control, we'll have some deviations transiently. So let's calculate VA limit and then DA limit, and then we're ready to calculate this slope value right here, which is what we're going to use in the simulation to limit the rise of duty cycle between 0 and DA limit. So plugging in the numbers, DA limit is equal to RA hat times IA limit plus KE hat times omega m star. And that is 0.15 times 145, or 144 is what I put in the problem, so we could also say that's 144 plus 2.15 times 188.5. This total quantity here is divided by VDC, which is 650. So the final result for DA limit is 427 divided by 650, or 0.657. And the last step is to find the slope, and that will be the DA limit divided by T ramp of omega. So we know that T ramp of omega is 0.6047 and DA lim is 0.657. Therefore, D slope equals 0.657 divided by 0.604, and that is 1.09, 1 over a second. And that's our final answer to problem 1F. So I'm going to now take you through the simulation that I have built to support this homework. We're going to skip over problem 2, which addresses the open loop and closed loop gains of the system, and just go on to problem 3, which is follows right on with what we just discussed. So we're here on problem number 3, where you're asked to develop a MATLAB Simulink model for an AC-fed, full-bridge, DC-fed, unipolar PWM controlled DC drive, having all the parameters given in problem number 1. It simulates ramping up to rated speed by ramping up duty cycle to the value found in problem, actually it's 1F, not 1C here. Apologize for that. And you can use this to verify all the results of problem 1 through all of these problems here. I have to go back and review why I said exactly these numbers, but it's pretty straightforward down here. This is what you want to do. You want to, also I asked you to provide simulation results in PDF form. James and I noticed that you uploaded your models, and I'm going to ask you please not to do that. I don't want to run everybody's models. I can tell whether you understand it by seeing the results, and that these are those results. Plot the armature current, armature voltage versus the back EMF voltage, plot the armature current, plot the torque that's applied to the motor end of the shaft, plot the mechanical speed, and try to see what insights you gain, and we're going to talk about those now. So let's go through my model. First of all, I am using, under the Simscape library, I'm using the Specialized Power Systems sublibrary under Electrical. And the main things that I'm using out of here are the DC machine and the measurement blocks, which are down here. So I'm using a voltage measurement here. I didn't need to have any current measurements because I can get those right from the DC block. I want to show you something about this. First of all, when you use the Specialized Power Systems, you need to use this Power GUI. Let's talk about setting up the simulation. In the Power GUI, this thing is going to run faster if you use the discrete type of simulation solver, and a sample time of 0.5 e to the negative 6 would give you a more than sufficient resolution for any simulation that has power electronics. But I'm going to even try to speed things up by changing this to 2, and let's see what happens there. If it doesn't, I'm going to go back to 0.5. I set up a stop time of 1 second. This is after a lot of playing around with this thing, and that's really what you kind of have to do to get your simulation right. There's a lot of messing with it. It's not just a simple thing to spend 1 hour on. I would expect getting the simulation working the first time, and to really get it working correctly, it would take you several hours. It took me several hours to make it working in a satisfactory way. I don't expect everyone to get the the exact results the first time. But I do expect you to have at least set it up um, to have the ramped voltage being applied to this motor. The other thing is, if you okay, in the modeling part tab here, you want to set your model up. The model settings really control the simulation solver. You're going to want to have a stiff solver, and so what you would pick is a variable step solver using the ODE23TB stiff solver. If you pick these other ones here, it's going to take a long time to run. So you want to take OD23TB, and I haven't ever used these two here. I don't have this one. You wouldn't use unless using Simscape. I'm not sure about this one here. But what I do is I set it up here, and then I set the GUI. You could set it to continuous right here, but it would take much longer to run. So discrete is more efficient. I hope those are little tricks that will help. I want to talk about the motor here. So this is a permanent magnet motor, and I expect you to pay attention to that. It has field type. If you pick the wound field type, you're going to have to come up with extra parameters, and you're going to have to apply a field source. It's challenging to get all these parameters right. I really still don't know how to do it correctly. And the problem with any simulator that uses components and that they have set up themselves, it's hard to understand what's under the hood. You can go under and look and figure it out, but I've not bothered with that because to me, simulating the field, it's going to cause a really long simulation time, and if you're going to do it correctly, and I don't want to mess with that. Okay, so if I hit this, what I'm talking about, if you hit OK, now the field winding appeared, and you'd have to apply two sources, one for the armature and one for the field. But we're skipping that. We're going to the permanent magnet field type. If you look at the parameters, then everything that was in the homework you can enter in. There's a little nuance here that you can decide. You remember, let's see, it's right here. You remember that I said that if you're using SI units, torque constant KT and back EMF constant KE are the same number. But if you pick back EMF constant to enter as your parameter, it's going to put it in volts per RPM. So you would be putting in a different number than the torque constant. And it's kind of weird because this is a SI unit and this is a mix. Actually, it's not even SI. I don't know what uses minutes. This is typically what you'd find on a data sheet, though, volts per RPM. But I didn't want to hang you up by going through that a lot in the class. Okay, so we have our machine. Everything's set up here. Let's look at how I did the synthesis of the voltage ramping, because that's really what this homework problem number 1 and this lecture is all about. So this sets the enable time, the time to start the motor. You could set start time to 0, but I always give a little bit of a delay. So I have a unit. This is a unit function here, or a step function. It outputs a step from 0 to 1. I could have put this step from 0 to the duty cycle that I'm trying to achieve, but I would only really be able to effectively do it this way out at this side of the simulation for one step. So I'm going to show you how I would do multiple. First of all, this is an enable. It's not controlling the waveform. It's a time at which you say, okay, let's start executing the pulse width modulation. This is like a enable, it's like a start signal, and then this same signal enables the pulse width modulation, and then you can start producing pulsed waveforms. So here's where we synthesize this, and I'm going to compare two different ones in another, probably the next lecture. So what I do is I say, okay, we bring in the start-stop signal. Everything's 0 coming out of here until I get to this point here, and I'm multiplying. Now what I had to do ahead of this is any signal that is a step, it for some reason it can't really produce a signal that you can do math on. So I add this transport delay. It's say 100 microseconds. That would correspond to the propagation delay of your microprocessor or digital signal processor, whichever one you're using. 100 microseconds is a decent number to assume there. And then what I'm saying is this is the first part of the square trajectory that I'm applying to my controls. Now remember what I mean by that. Let's go back to our the description leading up to this. So recall that I said you're going to step. This would be what I'm calling dA star in the simulation. I'm going from 0 to dA star. Okay, so going back to the simulation, I'm going to apply what comes out of this. This has to go through this transport delay to the ramp limiter. And this is where we put d-slope, or I'm calling it d-slope omega, because I also came up with a d-slope I, which is the fastest slope that you can really apply to the motor. This one is a relatively slow one, derived from the ramp-up time. So it gets multiplied by start-stop signal. This will make this go from 0 to the D star command, or the DA lim command. So one thing, maybe actually this is mislabeled. I'm going to call this DA lim, so it matches the simulation. Okay, then I'm going to put this signal out here, but then I want to create the other. I can keep adding changes in command, and the next thing that I will show you is how to create, say, ramping it up, ramping it down, ramping it negative, doing full 4-quadrant behavior. But I have to come up with a delta D, which is I calculate this in all of these are calculated in a MATLAB call function. It's start time, but it has to add to that the T ramp up time that we calculated. And so at that point, this here will add a little delta onto the prior command trajectory, delta D1. And then I'm going through the D slope I in this case, which is the fast slope. These add together to create the entire trajectory, and then I multiply it times the rated DC voltage to give a commanded armature voltage trajectory, which is shown in here. And now I'm going to show you my MATLAB. Well, first let me show you this in the simulation. One more thing I do in the model settings is I go to the model properties and I have callbacks that I define. So what that does is you can actually automatically execute a MATLAB function. You could do it. I don't really know the difference between init function and start. I think we could put what I'm going to show you in either one of those, but there's different functions that you can, where you call MATLAB code. So when we initialize everything, actually this simulation step I'm not using, so I'm going to take it out. I don't think I'm using it anywhere, but we can double check that. And then I'm calling this MATLAB function here. Okay, so the MATLAB function is this right here. I wrote it and I do all the calculations here. In fact, you can do your simulations. You can come up with the answer, say, to problem 1. And that's what I did in this MATLAB file here so that I didn't make any mistakes. And I'm going to post this on Canvas. So basically I wanted to show you, here I do all the controls commands, and I have a VA star 1, which is ramp up from 0 to basically to a rated, or to get the speed up to rated with our feed forward trajectory. This one is to go down all the way from the rated to 0, but I haven't done anything with that yet. This is the VA limit, but I'm going to change it to 145, although you'll see that it's not going to make any difference in the end. And I find the time to ramp up on the speed. That is, where is it? Here it is. T ramp up speed. So this is exactly the equation I described. We call this is what I was calling TE lim, but in this case I'm calling it TE star 1. And then there's also a time to ramp up or ramp down the current, and that is based on L di dt. Okay, so I get the ramp there, and then from that I come up with a d slope of the speed. It's the dA star 1, which is calculated here, and the t ramp up omega, which we calculate right here. And then the slope of the current is d star 1 divided by t ramp I. Okay, so you can see everything that's in this file, and I'm going to have to stop this part of the lecture at this point and give you a part 2 because I'm run out of time. But I'm going to just try to run this thing and see, make sure it runs. So I'm going to just hit, and basically just to also just show you one other thing. So all of this is in the synthesize. In the controls, we're doing open loops, so there's really nothing in here except when there will be a lot more when you add the closed loop. So this is just creating an enable to do the pulse width modulation and start switching, and then this is taking the voltage command and actually dividing it by VDCR to get the duty cycle. Now we could have skipped this step if I hadn't multiplied the thing earlier. It's just a matter of style, and I'm just trying to separate out the separate blocks here. And then these are the gate. This is the pulse width modulation. This is what you should have done in the first problem, homework 2. It should look something like this. Produces the 4 signals that go to the devices here. We have the DC link. I also have a dynamic break, which we haven't been able to talk about yet. Hopefully I can get through all the rest of this in one more lecture, and we can then pick back up on the AC motor drives. And then the motor, this is my source. This is the load, which we don't have a load connected yet, but I'm going to show you that in the next recorded lecture. You can see the whole simulation. This is the scope I would look at my results for. So let's run it, and hopefully it executes. If it doesn't, I know why. So let's see what happens. Okay, it looks like we're in good shape. There we go. Okay, so I see this, everything was successful, and I can click on this scope and we can see at least the start of the simulation. I'm going to have to show you the simulation. I think I removed a couple of signals here. Oh, there we go. Okay, so this is the startup time. I have my speed. Okay. Yeah, there we go. Okay, so the orange signal here is the VA star, and no, it's not the VA star, it's the actual voltage of the armature. So this orange signal is the armature voltage, and the green signal is the back EMF, and it would actually track with the speed. So you can see that everything's ramping up here. At this time right here at 0.6, we will have, and so we go from, well, it's right around here because we have this delay. So it's somewhere around here. It's going to reach the rated speed because we pre-calculated the ramp time, and then we are going to quickly drop the duty cycle back to what would give us the rated, well, in the case of this simulation, we don't have a load at all. So the duty cycle is simply just going to be calculated from the back EMF without any voltage drop across the current. So basically it was all pre-calculated ahead of time, and you can see that the speed is heading up. But one thing, and this is the important point, this is the current here. What we wanted the current to do when we started to switch was to go up to about 144 and be flat and stop. Well, see, it's not doing that. It's overshooting, and then it's coming back down, and then it shoots up again, comes back down, up and down. And this behavior here is, it's a resonant behavior where the time, basically I'm not sure really how to explain this, but it has to do with the resonant frequency that we're going to calculate in problem number 2 that would create this behavior here. And the only way we can fix it is to have closed loop control on the armature current. This blue line here is the load. We're at no load, so it's 0. And we're heading up there to where we want it to be. Let me just see if we can wait a few minutes and get to this point here. So you can see that there's some delay. It's not happening as fast as we expected, but we start to come down towards the no load current right here around just before 0.7 seconds. We were expecting a time of 0.604 from our startup time, so probably the speed should have hit the point of 188.5, which is this speed right here, and we're only reaching that because see, this is where, let's kind of zoom in on this. See, the duty cycle, this is heading up to the DA limit, and then it's going down to the D command, which is really the duty cycle that we calculated that you would need to have under rated conditions. We still want that duty cycle because it corresponds to the speed that we want. So we're actually not, we're a little bit over, and I think that might be because of the way I calculated things. But this is all open loop. So everything that I'm producing is based on pre-calculated feed-forward trajectory, which is really has a lot of estimates in it. It's not the real model. The way to do this even open loop and to hit the exact point that we want to, because we're off by a couple of radians here, and that's probably because I used the DA rated instead of using a DA no load. I think that's what I did here. So I assumed I had a rated current, and that pushed this up, but I could have fixed that by changing my duty cycle to simply being the estimated back EMF constant, KE, times the rated speed when I was calculating the duty cycle at steady state, and then I would have exactly hit the speed I wanted to get to. Okay, so that's all, and I'm hopefully will get this posted very soon. Thank you.